Hello, welcome back my student. Lecture 5, Digital Image Processing, EC 703A. Shongita Roy, Assistant Professor, Electronics and Communication Engineering Department, Narula Institute of Technology. Content: Transform of digital images, Inverse Fourier Transform, First Fourier Transform. Convolution. Now this is the basic formula of convolution. Ft one function, ht another function. These are two functions and it is with continuous variable t. Now if we convolve these two functions, then convolution sign is indicated by this asterisk mark, and this ft convolution ht is equal to the summation of these two functions with a particular small deviation tau. It is indicated by integration minus infinity to infinity f tau ht minus tau d tau, and it is integrated over minus infinity to plus infinity. Now this convolution in time domain, it will be how it will look in the frequency domain, that is indicated by Fourier transform. And the Fourier transform is represented by this double integration f tau ht minus tau d tau e to the power minus j twice by mu or omega, whatever it is, mu t dt. So as it is double integration, so we can interchange this two operator. So after interchanging the operator, we are getting this new equation, integration minus infinity to infinity f tau integration minus infinity to infinity ht minus tau e to the power minus j twice by mu t dt d tau. Now we can again write this inside integration. We can write ht minus tau integration d tau can be represented by, in the frequency domain it is h mu or h omega. So the integration, total integration is equal to integration minus infinity to infinity f tau h mu e to the power minus j twice by mu t d tau. So this can be represented by h mu or h omega is taken out as it is not within this integrable. So we are getting integration minus infinity to infinity f tau e to the power minus j twice pi mu tau d tau. So the second term is represented by frequency domain f omega or f mu. So the convolution in time domain of, in the frequency domain, it is the multiplication. Now this particular equation here, it is known as the one half of convolution theorem. Another half of convolution theorem, it is the reverse of this, that is to ft ht multiplication, it will be in the frequency domain, it will be convolution. Same thing but reverse. So ft ht in the frequency domain will be represented by h omega convolution f omega. 2D discrete Fourier transform and its inverse. So DFT, 2D DFT is represented by this equation. There are function fxy, it is x is ranging from 0 to m and y is ranging from 0 to n. So this is represented by this formula f uv is equal to summation of x is equal to 0 to m minus 1 summation of y is equal to 0 to n minus 1 function of xy e to the power minus j twice by ux divided by m plus vy by n, where fxy is a digital image of size m into n. So this will be represented finally 1 by mn integration summation u is equal to 0 to m minus 1 summation v is equal to 0 to n minus 1. So the this is represented nothing but in the frequency domain. It is represented in the frequency domain f uv e to the power minus j pi ux by m plus vy by n. Given the transform FUV, we can obtain Fxy by using the inverse discrete Fourier transform. And these two are known as 2D discrete Fourier transform pair. These two. So if it is Fourier transform, this is represented by this, and this is the reverse of this. Therefore, this is from time domain to frequency domain, and it is the reverse from frequency domain to time domain. Now, this is an example. This is a corrupted image with sinusoidal interference, and how it is looking in the frequency domain or Fourier. After Fourier transform, we are getting this magnitude. Now this figure is showing mask used to eliminate the energy burst, means this sinusoidal interference is removed by this mask, and the result is showing by this, and this is courtesy by NASA. Now this is how it is we are operating this. So this is the spatial domain information. Finally, again it is spatial domain information, but these two functions are not equal. So if this, after some operation, we are getting this final operation, that means modified or rectified. So this function in the time domain is transformed to frequency domain, then some operation is performed over that, then again it is inverse transform, then we are getting back the original image with rectified form. So here it is an example how the transform is operated. It is a bright spot within a black image, and it is spectrum is like this, and it is the central part, and its spectrum like this. This is the central part. This central part is this, and the black, and after that result showing increased details after log transformation. If we want to do directly frequency domain operation, then we cannot able to find the detail. So after stretching using log transformation, we are getting the spectrum in the frequency domain. This is the same figure but different type of transformation. So the figure, originally the figure, the bright spot was in the center, but here it is shifted, means translated. So the spectrum will be almost same, but if it is rotated, spectrum will be also rotated. It was vertical and horizontal spectrum, but here it is 45-degree rotation is there, as the figure also rotated over there. Now visualization of the Fourier transform. It is a rectangular function, so its corresponding Fourier representation is like this. Therefore, it is the magnitude of this function. So Fourier transform of some simple shapes. It is the shape and corresponding spectrum. It is a round shape, corresponding spectrum. It is a cross shape and its corresponding spectrum. Now fast Fourier transform. The main advantage of having fast Fourier transform or FFT is we can design FIR filters, and it is very simple, and it is given by this, some idea about this FFT. In the earlier DFT method, we have seen that the computational part is too long, means it was very time consuming, as well as it is memory space also huge. We want to reduce that. This can be done through FFT or fast Fourier transform. So we can say FFT is nothing but computation of discrete Fourier transform in an algorithmic format, where the computational part will be reduced or reduced as much as possible. So it is a kind of optimization. So these are the references, and thank you. Bye bye. Have a nice day.